All right, so we're going to take a slight aside in the book and talk about the Galois groups as permutation of the roots, something we saw in chapter 8, but I just want to quickly remind you. So in the situation of the quadratic extensions that we have, if this guy arose as the splitting field, or arises as a splitting field in a lot of different ways, but one of the ways it arises as a splitting field is of the polynomial t squared minus 5. Now, since elements of the Galois group, so sigma in the Galois group of q adjoining root 5 over q, since this sigma fixes q, it fixes the coefficients of t squared minus 5. So we know that when we plug in root 5 squared minus 5, we get 0. But if we apply sigma to both sides, well, the coefficient of 1 is not changed, and the coefficient of minus 5 is, or a 5 on the negative 5 on the constant is not changed, and the 0, of course, is not changed. We're really just applying sigma to whatever we plug in. So sigma of root 5 is still, when we plug that in, we still get a 0. So it's still 0 on the right? It's that 0 stays. And so what this is saying is sigma sends one root to another root, right? It doesn't send it to a non-root. Sigma moves roots around. And in fact, it doesn't move roots around. We have a better way of saying it. It permutes the roots. It does it in a bijective way. So if we were to label the roots, so let's let 1 correspond to root 5 and 2 correspond to negative root 5. What does sigma do? Sigma is the I negate you function. So if we want to think about this as a permutation, like we did in class a while ago, 1, the root that corresponds to root 5, is, the number that corresponds to root 5 is a 1, and the one that corresponds to negative root 5 is a 2. 1 should go to 2, and then where does 2 go? Well, if we negate root 5 again, it goes back. So then 2 goes back to 1. And under this setup, identity corresponds to, of course, the trivial permutation, which we often just write as E, the trivial permutation. So this is a way in which we can view elements of the Galois group as a subgroup of the symmetric group on 2 letters. And then, of course, in this case, just the Galois group of q adjoining root 5 over q is just the whole symmetric group on 2 letters. Let's go up really quick to the example we did earlier, where we had, let's see, our polynomial was t squared minus 2, t squared minus 3. This is order 4, so we're going to have 4 roots in this case. And let's label our roots in a helpful way. So let's revisit that example in relabeling. Let's look at, just be clear what we're looking at. And this is, of course, as a splitting field of t squared minus 3, t squared minus 2. We're going to label our roots. It doesn't matter how you label it. Okay, there's not a God-given way of doing this. I'm going to say 1 corresponds to root 2, 2 corresponds to negative root 2, 3 corresponds to root 3, 4 corresponds to negative root 3. All right, and then we had what? Well, we had our identity element, which of course corresponds to the identity. We have the element sigma 2, which negates root 2. So how would we write that as a permutation? Well, 1, it gets sent to 2 under negating root 2. And then 2 gets sent back to 1 under negating root 2. So we leave that alone. And the root 3's are fixed. So 3 and 4 nothing happens. So instead of writing 3 and 4 like this, we often will omit them entirely. This is just 1 goes to 2. Similarly, sigma 3 is going to be just 3 goes to 4, 4 goes back to 3. We're not going to write out the 1 is fixed and the 2 is fixed. And then sigma 2, sigma 3 is, of course, well, we have to do both 1, 2, and we have to do the transposition 3, 4 as well. And so as a subgroup of the symmetric group, we can view the Galois group of Q adjoin root 2, root 3 over Q as isomorphic to the subgroup of the symmetric group generated by 1, 2, and 3, 4 separately. That subgroup is, of course, just the identity 1, 2, 3, 4, and 1, 2, 3, 4. In general, after labeling the roots, as we've done in this example, the Galois group of some extension, where L is the splitting field of F, some polynomial F over K, is a subgroup of the symmetric group on n letters, where n is the degree of F. So here our guy was of degree 4, it was a quartic, and we were naturally a subgroup of S4. So we'll often do this. We'll often implicitly identify our Galois group as a subgroup of some symmetric group, and we'll just pick a random labeling usually. We'll say what the labeling is, but there's no rhyme or reason behind it usually. All right, so a quick aside on that.